Hello there, and welcome to the Sleepy Library. It's lovely to have you here with me tonight. Before we begin this gentle journey through the science of weather, I'd love to know where in the world you're watching from. Are you tucked into bed listening to rain against your window? Perhaps you're somewhere warm and still, watching clouds drift past. Wherever you are, I hope you're comfortable, safe, and ready to let your mind wander through the peaceful mysteries of the atmosphere. If you enjoy these relaxing explorations of science, a like and subscribe truly helps this little channel grow. And to those of you already here with us, thank you from the bottom of my heart. Your presence means everything. Tonight, we're going to explore something that touches every single moment of your existence, yet often passes by without much thought. The weather. That gentle breeze through an open window. The way clouds gather before afternoon rain. The crisp coolness of autumn air. Weather is the atmosphere speaking to us in a language of temperature and movement, moisture and pressure. And while we often take it for granted, the science behind weather is extraordinarily beautiful. A story of energy from the sun, water changing forms, air moving across continents, and the earth itself spinning beneath it all. So settle in, let your breathing slow, and allow yourself to drift through these facts as gently as a leaf floating on a stream. There's no need to memorize anything or grasp every detail. Just let the words wash over you, painting pictures in your mind of the beautiful, complex, and endlessly fascinating atmosphere that surrounds us all. Weather is simply the short-term conditions happening in the atmosphere at any given moment. It's the answer to questions like, how warm is it outside? Is it sunny or cloudy? Is rain falling or snow gathering? Will the wind blow gently or strongly today? These conditions change constantly, sometimes hour by hour, sometimes minute by minute. Weather is different from climate, which describes the long-term patterns over years and decades. Weather is immediate, personal, and ever-changing. The atmosphere itself is a thin layer of gases wrapped around our planet like a delicate blanket. It extends upward for many miles, gradually thinning until it fades into the emptiness of space. This blanket is made mostly of nitrogen and oxygen, with smaller amounts of other gases mixed in. It's this mixture that we breathe, that protects us from harmful radiation, and that creates all the weather phenomena we experience. Within this atmospheric blanket, several key elements work together to create weather. Temperature tells us how warm or cool the air feels. It changes with the time of day, the season, and where you are on Earth's surface. Air pressure describes the weight of all that air pressing down from above. Though we rarely notice it, this pressure is always there, and changes in pressure are one of the main drivers of weather patterns. Humidity measures how much water vapor is floating invisibly in the air around us. Wind is simply air in motion, flowing from one place to another. Clouds are collections of tiny water droplets or ice crystals suspended high in the sky. And precipitation is water falling from the sky in various forms, whether rain, snow, sleet, or hail. But why does weather exist at all? Why doesn't the atmosphere just sit still and unchanging? The answer lies in something beautifully simple. The sun doesn't heat the earth evenly. Different parts of our planet receive different amounts of solar energy. The equator, where the sun's rays strike most directly, receives much more heating than the poles, where sunlight arrives at a slant. Ocean surfaces absorb heat differently than land surfaces. Mountains cast shadows, while valleys bask in sunlight. Dark forests absorb more warmth than bright deserts. This uneven heating creates differences in temperature throughout the atmosphere. And nature, in its endless quest for balance, tries to even things out. Warm air rises in heated areas, while cooler air sinks in others. Air flows from regions of high pressure toward regions of low pressure. Water evaporates from warm surfaces and condenses in cooler areas. All of this movement and change, this constant attempt to redistribute energy across the planet, is what we experience as weather. Let's follow a single drop of water on its journey through the weather cycle. Our story begins in the ocean, though it could just as easily start in a lake, a river, or a puddle on a sidewalk. The sun rises over the water's surface, and its warm rays begin to heat the liquid below. As water molecules absorb this energy, they start to vibrate faster and faster. Eventually, some gain enough energy to break free from the liquid surface altogether, transforming from liquid into an invisible gas called water vapor. This process is called evaporation. The newly freed water vapor is lighter than the surrounding air, so it begins to rise. Up and up it floats, carried by warm updrafts, climbing higher into the atmosphere. As it rises, something important happens. The air around it grows cooler. This is because air pressure decreases with altitude, and as the air expands, it cools down. The higher our water vapor climbs, the cooler its surroundings become. Eventually, the rising water vapor reaches an altitude where the air is cool enough that the vapor can no longer remain a gas. It needs something to cling to, and fortunately, the atmosphere is full of tiny particles. Dust, pollen, sea salt, even microscopic bits of smoke. These particles, though invisible to our eyes, serve as surfaces where water vapor can condense back into liquid droplets. Each particle becomes the center of a tiny water droplet, so small that it would take millions of them to make a single raindrop. These countless tiny droplets, all floating together in the sky, are what we see as clouds, light enough to remain suspended in the air, buoyed by gentle updrafts. But they don't stay separate for long. In the turbulent environment of a cloud, droplets bump into each other constantly. When they collide, they sometimes stick together, forming slightly larger droplets. These larger droplets have more collisions, growing bigger still. This process, called coalescence, continues as long as the droplets remain in the cloud. Meanwhile, the temperature continues to matter. In colder parts of the cloud, some droplets freeze into tiny ice crystals. These ice crystals have an interesting property. They can grow by stealing water vapor from nearby liquid droplets. The crystals grow larger while the droplets shrink, a process that helps create precipitation in many clouds. Eventually, whether through coalescence or the ice crystal process, droplets grow large enough that they can no longer be held aloft by the air currents. Gravity takes over, and they begin to fall. As they fall, they may pass through warmer air and melt into raindrops, or they might remain frozen and fall as snow or sleet. Sometimes, in particularly turbulent thunderstorms, drops can be carried up and down repeatedly, freezing into layers like an onion, eventually falling as hail. If conditions are just right, our raindrop falls gently through the air, joining countless others in a light drizzle or steady rain. It might land in a field and soak into the soil. It might splash into a stream and flow toward the ocean. Or it might land on a warm surface and evaporate once again, beginning the cycle anew. The same water has been making this journey for billions of years, cycling endlessly between ocean, sky, and land. This cycle has many names: the water cycle, the hydrologic cycle. But regardless of what we call it, it's one of the most essential processes on our planet. It distributes fresh water across continents, fills rivers and lakes, provides the moisture that plants need to grow, and creates the rain and snow that shape our landscapes. And all of it happens because of the simple interaction between water, energy from the sun, and the changing temperature of the atmosphere. Now let's turn our attention to another fundamental element of weather: wind. Wind is air in motion. But what sets the air moving in the first place? The answer, once again, comes back to uneven heating and the resulting differences in air pressure. Imagine a sunny morning on a beach. The sun rises over the ocean, and its rays begin to warm both the water and the land. But here's something interesting. Land and water don't heat up at the same rate. The solid ground of the beach absorbs heat quickly. Sand particles warm up, and that heat transfers to the air just above the surface. The air grows warmer, becomes less dense, and begins to rise. As it rises, it leaves behind an area of lower pressure near the ground. Meanwhile, out over the ocean, the water is also absorbing sunlight. But water has much higher heat capacity than land, meaning it takes more energy to raise its temperature. The ocean surface warms up much more slowly. The air above the water remains relatively cool and dense, creating an area of higher pressure. Now we have a situation: high pressure over the ocean, low pressure over the land. Nature doesn't like pressure differences, and it immediately begins to correct the imbalance. The denser, higher pressure air over the ocean begins to flow horizontally toward the lower pressure area over land. This flowing air is what we feel as wind. In this case, it's called a sea breeze, and anyone who has spent time at the beach on a warm day knows this cooling wind well. But the story doesn't end there. The air that rose over the warm land has to go somewhere. High in the atmosphere, it flows back toward the ocean, completing a circular pattern. Eventually, it cools, becomes denser, and sinks back down over the water. This creates a complete circulation loop, with air rising over the land, flowing toward the ocean aloft, sinking over the water, and flowing back toward the land near the surface. At night, the pattern reverses. Land cools down much faster than water after sunset. The air over the land becomes cooler and denser than the air over the ocean. Now the high pressure is over land, the low pressure is over water, and the wind flows from land to sea. This is called a land breeze, and it tends to be gentler than the daytime sea breeze. This same principle operates on much larger scales. Mountains and valleys create their own wind patterns as slopes heat and cool at different rates. During the day, the sun warms the mountain slopes, creating updrafts that flow up the mountainside. At night, cooler air drains down into valleys like water flowing downhill. These mountain and valley breezes can be quite strong, and they play important roles in local weather patterns. But wind doesn't just flow in straight lines from high pressure to low pressure. The Earth itself is spinning, and this rotation adds a twist to the story, quite literally. As air begins to flow across the planet's surface, the rotation of the Earth beneath it causes the wind to curve. In the northern hemisphere, winds curve to the right of their intended path. In the southern hemisphere, they curve to the left. This deflection is called the Coriolis effect, named after the French mathematician who first described it. The Coriolis effect is why large-scale weather systems tend to rotate. Low-pressure areas, where air is flowing inward, develop a counterclockwise spin in the northern hemisphere and a clockwise spin in the southern hemisphere. High-pressure systems spin in the opposite direction. This rotation is subtle at small scales, but becomes increasingly important as we look at larger weather patterns. On the grandest scale, the uneven heating between the equator and the poles drives enormous circulation patterns that span entire hemispheres. Near the equator, Intense heating creates rising air and a belt of low pressure. This rising air flows northward and southward at high altitudes, eventually cooling and sinking back down around 30 degrees latitude north and south. This creates belts of high pressure in these subtropical regions. Air at the surface flows back toward the equator, creating the trade winds that sailors have relied on for centuries. The Coriolis effect curves these winds, making them blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. Further north and south, between about 30 and 60 degrees latitude, surface winds generally flow toward the poles. These are the prevailing westerlies, and they're the winds that carry most weather systems across the mid-latitudes where many people live. Near the poles themselves, cold, dense air sinks and flows outward, creating the polar easterlies. These global wind patterns, combined with local effects and the Coriolis deflection, create the complex tapestry of winds that move weather systems around our planet. Look up at the sky on any given day, and you'll likely see clouds. They might be puffy and white, thin and wispy, dark and threatening, or spread across the entire sky in a uniform grey blanket. Clouds are one of the most visible and recognizable features of weather, and they have stories to tell if we know how to read them. Clouds form when water vapor in the air condenses into tiny liquid droplets or ice crystals. But not all clouds are created equal. They form at different altitudes, under different conditions, and they tell us different things about the current and future weather. Scientists have classified clouds into several main types based on their appearance and altitude. Let's start with the clouds that form highest in the atmosphere. High up, typically above 20,000 feet, the air is very cold. Clouds that form at these altitudes are made primarily of ice crystals rather than water droplets. The most common high cloud is the cirrus cloud. Cirrus clouds look like delicate wisps or strands, often curved or feathery in appearance. They're made of ice crystals, and they're so thin that sunlight passes through them easily. When you see cirrus clouds, they often indicate that the weather is currently fair, but they can also be harbingers of change, sometimes appearing as the first sign of an approaching weather system. Another high cloud is the cirrostratus, which forms a thin, transparent veil across the sky. These clouds can cover the entire sky, but are so thin you can still see the sun or moon through them. In fact, cirrostratus clouds sometimes create beautiful halos around the sun or moon as light bends through the ice crystals. The appearance of cirrostratus often means that rain or snow might arrive within the next day or so. There's also cirrocumulus, which appears as small white patches or ripples high in the sky, sometimes called a mackerel sky, because the pattern resembles fish scales. At middle altitudes, roughly between 6,000 and 20,000 feet, we find clouds with the prefix alto. Altocumulus clouds appear as grey or white patches or layers, often with some darker shading. They might form in lines or waves across the sky. These clouds generally indicate fair weather, though if they appear on a warm, humid morning, they might suggest thunderstorms later in the day. Altostratus clouds form uniform grey or blue-grey sheets across the sky. Unlike cirrostratus, altostratus clouds are thick enough that the sun appears as a dim disk behind them, like looking through frosted glass. These clouds often signal that steady rain or snow is on the way, usually arriving within the next several hours. There's also nimbostratus, dark grey clouds that form a thick, wet-looking layer across the sky. These are the clouds that bring prolonged rain or snow. Nimbus, or nimbo, always refers to rain-producing clouds. Low clouds form below 6,000 feet, often close enough to the ground that you could walk through them if you climbed a modest hill. Stratus clouds are perhaps the most uniform and featureless clouds in the sky. They form low grey sheets that can cover the entire sky, creating overcast conditions. Stratus clouds might produce drizzle or light snow, but they usually don't bring heavy precipitation. When stratus clouds form at ground level, we call them fog. Stratocumulus clouds are low, lumpy clouds that form in patches or layers. They're darker grey than regular cumulus clouds and often cover most of the sky, though you might see breaks of blue between the patches. These clouds rarely produce more than light rain or drizzle. Then we have cumulus clouds, the classic puffy white clouds that children love to draw. Cumulus clouds look like cotton balls or cauliflower florets, with flat bases and rounded tops. They form on days when the sun heats the ground unevenly, creating updrafts of warm air. Each puffy cloud represents one of these rising air currents. Small cumulus clouds with significant space between them indicate fair weather. The sky might be partly cloudy and the day pleasant. But cumulus clouds can grow. Given enough heat and moisture, they tower upward, piling higher and higher into the atmosphere. These growing clouds are called cumulus congestus, and they're often a sign that the atmosphere is becoming unstable. Under the right conditions, cumulus clouds can grow into something far more dramatic: cumulonimbus clouds. Cumulonimbus are the giants of the cloud world. They're the clouds that produce thunderstorms. A fully developed cumulonimbus can stretch from near ground level all the way up to the top of the troposphere, sometimes reaching heights of 40,000 feet or more. The top of the cloud often spreads out in a characteristic anvil shape as it hits the stable stratosphere and can't rise any higher. The bottom of a cumulonimbus is dark and ominous, often appearing nearly black. These enormous clouds are weather factories. Inside them, powerful updrafts and downdrafts create turbulent conditions. Water droplets are carried upward, freeze, fall back down, get caught in updrafts again, and accumulate layer after layer of ice. This process can create hailstones. The turbulent conditions also separate electrical charges, eventually leading to lightning. Heavy rain falls from these clouds, sometimes in intense bursts, and under certain conditions, cumulonimbus clouds can even produce tornadoes. By observing clouds, you can often predict what the weather will do in the next few hours. Thin, high clouds might mean a weather system is approaching. Thickening clouds at middle levels suggest rain or snow is getting closer. Dark, low clouds often mean precipitation is imminent or already falling. And towering cumulus, building up on a summer afternoon, might mean thunderstorms are on the way. Few weather phenomena capture our attention quite like lightning. A brilliant flash splitting the sky, followed seconds later by the rumble or crack of thunder. Lightning is both beautiful and powerful, and the science behind it is fascinating. Lightning begins inside cumulonimbus clouds, those towering thunderstorm clouds we just discussed. Inside these clouds, conditions are remarkably turbulent. Strong updrafts carry water droplets high into freezing temperatures, where they turn to ice. These ice particles collide with water droplets, with other ice particles, and with soft hail called graupel. Each collision transfers tiny amounts of electrical charge between the particles. The exact mechanism is still being studied, but scientists believe that smaller, lighter ice crystals tend to become positively charged, while larger, heavier particles like graupel become negatively charged. The powerful updrafts carry the light, positively charged ice crystals upward toward the top of the cloud. The heavy, negatively charged graupel either hangs in the middle of the cloud or falls toward the bottom. Over time, this process separates the charges within the cloud, creating a positive charge region near the top and a negative charge region in the middle and lower portions. Meanwhile, something interesting happens on the ground below the storm. The negative charges in the bottom of the cloud repel negative charges in the ground, pushing them away. This leaves the ground beneath the storm with a positive charge. Tall objects like trees, buildings and hills become especially positively charged because they're closer to the cloud. As the charge separation increases, the electrical field between the cloud and ground grows stronger and stronger. Air is normally an excellent insulator, preventing electricity from flowing easily. But when the electrical field becomes powerful enough, it can overcome this insulation. The atmosphere essentially breaks down, and a pathway forms for electricity to flow. This happens in stages. First, a stepped leader, a channel of negative charge, extends downward from the cloud in a series of short, quick steps. It's reaching toward the ground, branching and forking as it goes. The stepped leader itself is invisible to our eyes and happens far too quickly for us to see as separate steps. As this channel of negative charge approaches the ground, the positive charges below respond. Upward streamers of positive charge reach up from the ground and from tall objects, stretching toward the descending stepped leader. When a streamer and the stepped leader finally connect, usually just 100 feet or so above the ground, a complete electrical pathway exists between cloud and earth. Now comes the part we actually see. Electrons rush down this pathway from the cloud, but the visible lightning flash is actually a return stroke that travels upward from the ground along the path created by the stepped leader. This happens at a significant fraction of the speed of light, far too fast for our eyes to separate the components. What we see is a brilliant flash, typically lasting only a fraction of a second. But often, the first stroke doesn't discharge all the available charge. Additional leaders can travel down the same channel, each followed by its own return stroke. This happens so rapidly, typically within a few tenths of a second, that we see it as a single flickering flash. The multiple strokes are what give lightning its characteristic flickering appearance. Most lightning doesn't actually strike the ground at all. Roughly 75 to 80% of lightning remains within the cloud, jumping between different charge regions, or travels from one cloud to another. This cloud-to-cloud lightning is just as dramatic as cloud-to-ground lightning, though often less noticed because it doesn't pose the same direct risk to people and property. Thunder is the sound produced by lightning. The lightning bolt is incredibly hot, reaching temperatures of around 50,000 degrees Fahrenheit. That's 5 times hotter than the surface of the sun. This extreme heat causes the air along the lightning channel to expand explosively, faster than the speed of sound. This creates a shock wave that we hear as thunder. The reason we see the lightning before we hear the thunder is simple. Light travels much faster than sound. Light travels at about 186,000 miles per second, essentially reaching our eyes instantaneously. Sound travels much more slowly, at about 1/5 of a mile per second, or roughly 1 mile every 5 seconds. This is why you can estimate how far away a lightning strike is by counting the seconds between the flash and the thunder, then dividing by 5. If you count to 10 before hearing thunder, the lightning struck about 2 miles away. The sound of thunder varies depending on your distance from the lightning and the path the sound takes to reach you. Close lightning produces a sharp crack or boom. More distant lightning creates a long, low rumble as the sound waves bounce off clouds, hills, and buildings, reaching your ears along many different paths at slightly different times. Sometimes you can see distant lightning, but never hear the thunder at all, because sound dissipates over distance. This is sometimes called heat lightning, though it's no different from any other lightning. You're simply too far away to hear it. Lightning is dangerous. Each year, lightning starts thousands of wildfires, causes billions of dollars in property damage, and injures or ends the lives of hundreds of people. When you hear thunder, it's time to seek shelter. The old saying, "When thunder roars, go indoors," is good advice. If you're caught outside with no shelter available, avoid standing under tall, isolated trees, stay away from open fields and hilltops, and avoid water. While everyday weather brings gentle breezes and afternoon showers, the atmosphere is also capable of producing events of extraordinary power. These extreme weather events are among nature's most impressive and dangerous displays. Tornadoes are perhaps the most violent weather phenomena on Earth. A tornado is a rapidly rotating column of air that extends from a thunderstorm to the ground. The visible funnel we see is made of water droplets condensed by the low pressure inside the rotating column, along with dust and debris picked up from the ground. But the wind itself is invisible, and tornadoes can sometimes be hidden by rain or darkness. Most tornadoes form from supercell thunderstorms. These are rotating thunderstorms with a well-developed circular wind pattern called a mesocyclone. The rotation begins high in the storm, but under the right conditions, it can extend downward. Exactly why some mesocyclones produce tornadoes while others don't is still not fully understood. But it seems to involve temperature differences, the interaction between updrafts and downdrafts, and other subtle factors. The conditions that favor tornado formation include strong wind shear, where wind speed or direction changes rapidly with altitude. This creates rotation in the atmosphere. Warm, moist air near the surface provides energy for storm development, while cooler, drier air aloft creates instability. When a cold front pushes into warm, humid air, it can trigger intense thunderstorms, and if the other conditions are right, tornadoes can form. Tornado wind speeds can reach 200 to 300 miles per hour in the most intense storms, though most tornadoes are much weaker. A typical tornado might last only a few minutes and travel a few miles across the ground, though some exceptional tornadoes have lasted for hours and traveled over 100 miles. The width of a tornado can vary from just a few dozen feet to over 2 miles across. The United States experiences more tornadoes than any other country, with an average of about 1,200 occurring each year. Most form in an area called Tornado Alley, which includes parts of Texas, Oklahoma, Kansas, and Nebraska, though tornadoes can occur in all 50 states. They're most common in spring and early summer, when cold fronts from the north frequently clash with warm, moist air from the Gulf of Mexico. Tornadoes also occur in many other parts of the world, including Argentina, Bangladesh, and parts of Europe. Hurricanes are weather systems of an entirely different scale. Where a tornado might be a few hundred yards wide, a hurricane can span several hundred miles. Where a tornado lasts minutes to hours, a hurricane can persist for weeks. These enormous rotating storms form over warm tropical oceans and are fueled by the heat and moisture rising from the water surface. A hurricane begins as a cluster of thunderstorms over the ocean. When conditions are right, including water temperatures of at least 80 degrees Fahrenheit, these storms can organize into a rotating system. The Coriolis effect from Earth's rotation helps establish the rotation. As warm, moist air rises from the ocean surface, it creates an area of low pressure at the center. More air flows inward to fill this low pressure, but the Coriolis effect curves its path, creating a spiral pattern. The rising air releases heat as water vapor condenses into clouds, and this heat provides energy that powers the storm, causing even more air to rise. At the center of a mature hurricane lies the eye, a region of calm winds and often clear skies. The eye is typically 20 to 40 miles across, surrounded by the eye wall, a ring of the most intense thunderstorms and strongest winds in the entire hurricane. Outside the eye wall, spiral bands of thunderstorms curve outward for hundreds of miles. Hurricane wind speeds are categorized on the Saffir-Simpson scale, from Category 1 to Category 5. A Category 1 hurricane has sustained winds of 74 to 95 miles per hour, while a Category 5 has winds exceeding 157 miles per hour. These winds can cause enormous damage, tearing roofs off buildings, snapping trees, and turning debris into dangerous projectiles. But wind isn't the only threat from hurricanes. Storm surge, the rise in ocean water level caused by the storm, is historically the leading cause of harm from hurricanes. As the hurricane approaches shore, its powerful winds push water ahead of it, raising sea level by 10, 15, even 20 feet or more. This surge can flood coastal areas, demolishing buildings and washing away roads. The flooding can extend miles inland, especially in low-lying areas. Hurricanes also bring tremendous amounts of rain. Some hurricanes have dropped more than 50 inches of rain in a single location, causing catastrophic inland flooding far from the coast. Rivers overflow their banks, landslides occur on hillsides, and communities can remain flooded for weeks. Additionally, hurricanes can spawn tornadoes, usually in the outer rain bands of the storm as it makes landfall. Hurricanes form only over warm tropical oceans in certain parts of the world, called hurricanes in the Atlantic and Eastern Pacific, typhoons in the Western Pacific, and cyclones in the Indian Ocean and South Pacific. The hurricane season in the Atlantic runs from June through November, with peak activity in August and September when ocean waters are warmest. Climate change is affecting extreme weather events. Warmer ocean temperatures provide more energy for hurricanes to intensify. Rising sea levels make storm surge flooding more severe. A warmer atmosphere can hold more water vapor, leading to heavier rainfall from storms. While the total number of hurricanes might not be increasing, evidence suggests that the proportion of intense hurricanes is growing. Other forms of extreme weather include heat waves, prolonged periods of unusually hot weather that can have serious health impacts, especially for elderly people and those without air conditioning. When nights don't cool down, the body never gets relief from the heat. Flash floods occur when heavy rain falls faster than the ground can absorb it, or rivers can carry it away. Desert areas are particularly vulnerable because the hard, dry ground doesn't absorb water well. Blizzards combine heavy snow with strong winds and cold temperatures, creating whiteout conditions where visibility drops to near zero. Weather doesn't just happen on grand scales. Fascinating weather phenomena occur in small areas, sometimes over distances of just a few feet. This is sometimes called microweather or microclimate, and it reminds us that the atmosphere is always responding to local conditions. Cities create their own unique weather patterns. Buildings, roads, and parking lots are made of materials like concrete and asphalt that absorb more heat than natural surfaces. During the day, these surfaces soak up enormous amounts of solar energy. At night, they release this stored heat slowly, keeping the city warmer than surrounding rural areas. This is called the urban heat island effect, and it can make city centers several degrees warmer than nearby countryside. The urban heat island affects local wind patterns. Warm air rises over the city center, drawing cooler air in from the suburbs. This can create a gentle circulation pattern, with air flowing toward the city at ground level and away from the city at higher levels. The heat island also affects when and where precipitation falls. Some studies suggest that thunderstorms are more likely to form downwind of cities, triggered by the extra heat and moisture. Buildings also channel and accelerate wind. When wind blows against a tall building, it's forced to flow around the structure. This can create strong gusts at street level, especially at corners where wind from two directions converges. Some downtown areas are famous for their strong winds that make walking difficult on windy days. Building designers now consider these wind patterns to minimize uncomfortable wind tunnels. Vegetation creates its own local weather effects. A forest, typically cooler and more humid than an adjacent field. Trees provide shade, blocking sunlight from reaching the ground. They also release water vapor through their leaves in a process called transpiration. The combined effect of evaporation from soil and transpiration from plants, called evapotranspiration, can put significant moisture into the air, sometimes contributing to cloud formation and precipitation downwind of forests. Even a single large tree creates its own microclimate. Stand beneath a tree on a hot summer day, and you'll feel noticeably cooler than in direct sun. The tree's shade prevents solar energy from warming the ground directly. The tree also releases water vapor that can cool the surrounding air. On a still night, areas beneath trees can be warmer than open areas, because the tree canopy acts like a blanket, trapping heat radiating from the ground. Bodies of water moderate local temperatures. Water heats and cools more slowly than land, so areas near lakes or oceans experience smaller temperature swings. In summer, the water is often cooler than the land, creating pleasant breezes and preventing extreme heat. In winter, the water might be warmer than the land, keeping coastal areas milder than inland locations. This is why places like San Francisco, surrounded by cool ocean water, rarely get very hot, despite being at a low latitude. Snow cover dramatically changes local weather. Fresh snow is highly reflective, bouncing much of the sun's energy back to space rather than absorbing it. This keeps temperatures cooler during the day. Snow is also an excellent insulator. The air trapped between snowflakes prevents heat from escaping the ground. On a clear winter night, the coldest temperatures often occur where snow cover is thin or absent, while areas with deep snow stay slightly warmer because the ground heat is trapped beneath the snow layer. Topography creates countless micro-weather effects. South-facing slopes receive more sunlight than north-facing slopes in the northern hemisphere, making them warmer and drier. Valleys can trap cold air on calm nights, becoming much cooler than nearby hilltops. This is because cold air is dense and flows downhill like water, settling in low-lying areas. Frost often forms in valley bottoms first, and these areas are sometimes called frost pockets. Even your own backyard contains multiple microclimates. The sunny side of your house is warmer and drier than the shady side. A corner sheltered from wind creates a protected pocket that might allow sensitive plants to survive. A stone wall absorbs heat during the day and radiates it at night, creating a warmer zone nearby. Paying attention to these small-scale weather variations can help you understand your local environment better. The atmosphere doesn't just create wind and rain, it also produces some of nature's most beautiful optical displays. These phenomena result from light interacting with water droplets, ice crystals, and air molecules in various ways. The rainbow is perhaps the most beloved atmospheric optical phenomenon. Rainbows form when sunlight shines through water droplets in the air, usually during or just after a rain shower. When light enters a water droplet, it slows down and bends, or refracts. Different colors of light bend by different amounts, with blue light bending more than red light. The light then reflects off the back of the droplet and exits, bending again. This double bending and reflection separates the white sunlight into its component colors, creating the spectrum we see. For you to see a rainbow, the sun must be behind you, and rain or water droplets must be in front of you. The rainbow always appears opposite the sun in the sky. This is why rainbows are most often seen in late afternoon, when the sun is low in the west and showers are moving east, or in early morning, when the sun is low in the east and showers are to the west. Each person sees their own rainbow, because the light reaching your eyes comes from different droplets than the light reaching someone else's eyes. Sometimes you can see a secondary rainbow, fainter and with colors reversed, appearing outside the primary rainbow. This forms when light reflects twice inside the water droplets instead of once. The area between the primary and secondary rainbow often appears darker than the sky on either side. This region is called Alexander's band, and it exists because of the way light is distributed by the water droplets. Halos around the sun or moon are created by ice crystals high in the atmosphere. These crystals, typically found in cirrostratus clouds, are shaped like tiny hexagonal plates or columns. When light passes through these crystals, it bends by a specific angle determined by the crystal's shape. The most common halo forms a ring around the sun or moon at an angle of 22 degrees. Looking at this halo, you'll notice it has a reddish inner edge and a bluish outer edge, caused by the same color separation that creates rainbows. Sometimes, more complex ice crystal formations create other optical effects. Sundogs, also called parhelia, are bright spots that appear on either side of the sun, often at the same level as a 22-degree halo. They're caused by hexagonal plate-shaped ice crystals floating horizontally in the air. Light passes through specific crystal faces, creating these bright, colorful spots. Sundogs are especially vivid when the sun is low on the horizon. The blue color of the sky itself is an optical phenomenon. Sunlight contains all colors of the rainbow mixed together. As this light passes through the atmosphere, it collides with gas molecules. These collisions scatter the light in different directions. Blue light, having a shorter wavelength, is scattered more easily than red light. This scattered blue light reaches our eyes from all directions, making the whole sky appear blue. At sunrise and sunset, we see beautiful colors in the sky, especially shades of red, orange, and pink. This happens because the sun's light must pass through much more atmosphere when the sun is near the horizon than when it's overhead. As the light travels this longer path, blue light gets scattered away long before reaching our eyes, while red and orange light continues through. This remaining light creates the warm colors we associate with dawn and dusk. Clouds lit by this colored light become brilliant shades of pink, orange, and purple. On especially clear days, you might notice that distant mountains appear bluish. This isn't because the mountains are actually blue, but because of atmospheric scattering. The air between you and the mountains scatters blue light toward your eyes, making the mountains take on a bluish hue. The farther away the mountain, the more atmosphere between you and it, and the bluer it appears. Sometimes, just after sunset or before sunrise, you might see the sky glowing in beautiful shades of purple and pink. This is called alpenglow on mountains, or twilight colors in the sky. It happens because the upper atmosphere is still illuminated by the sun even after it has set below the horizon from your perspective. The light filtering through the atmosphere creates these ethereal colors. Mirages are another atmospheric optical effect. On hot days, a layer of very hot air forms just above a sun-baked road or desert. This hot air has a different density than the cooler air above it, causing light to bend as it passes through. Sometimes, this bending is severe enough that light from the sky gets bent toward your eyes, making it appear as if there's water on the road ahead. You're actually seeing a reflected image of the sky, but your brain interprets it as a puddle of water. As you get closer, the mirage moves away, always staying at the same distance ahead of you. Weather doesn't just exist in abstract scientific terms. It has profound effects on every living thing on Earth, including humans, animals, and plants. The relationship between life and weather is intricate and fascinating. Animals have evolved remarkable sensitivities to changes in atmospheric conditions. Many species can detect approaching storms long before humans notice anything unusual. Birds often become more active before a storm, feeding intensely to build energy reserves. This might be because they sense the dropping air pressure that signals an approaching low-pressure system. Some bird species fly lower before storms, possibly because their ears detect pressure changes, or because insects they feed on are flying lower. Fish respond to weather changes as well. Fishermen have long observed that fish feed more actively before storms. This might be related to changes in light levels as clouds move in, or to changes in water pressure, or even to the fish sensing vibrations from distant thunder. After a storm passes and air pressure rises, fish often become less active and harder to catch. Many insects change their behavior before rain. Bees return to their hives, ants seal their colony entrances, and termites may swarm. These behaviors might be triggered by increases in humidity, changes in light levels, or detection of electrical changes in the atmosphere. Spiders have been observed building stronger webs or moving to sheltered locations before storms, though scientists aren't entirely sure how they sense the approaching bad weather. Some people report that they can feel weather changes in their bodies. Those with arthritis often say their joints ache more when a storm is approaching. While this has sometimes been dismissed as folklore, research suggests there may be something to it. Changes in barometric pressure might affect the pressure of fluids in joints, causing discomfort. Changes in humidity can also affect how joints feel. Headaches and migraines are sometimes triggered by weather changes, possibly related to pressure variations or to atmospheric electrical effects. Humidity affects how comfortable we feel at any given temperature. On a humid day, our bodies have trouble cooling themselves through sweat evaporation. The air is already full of moisture, so sweat stays on our skin rather than evaporating. Since evaporation is what actually cools us, we feel much hotter than the temperature would suggest. This is why weather reports often include a heat index, combining temperature and humidity to show how hot it actually feels. In cold weather, humidity and wind make the temperature feel colder than it is. Wind constantly replaces the thin layer of warm air next to your skin with cold air, pulling heat away from your body faster than calm air would. This is measured as wind chill. High humidity in cold weather doesn't cool you the way it heats you in summer, but it can make the cold feel more penetrating because humid air conducts heat away from your body more readily than dry air. Plants are exquisitely sensitive to weather patterns. Their entire life cycle is timed around seasonal weather changes. In spring, warming temperatures and increasing day length trigger buds to open and flowers to bloom. The timing must be precise. Bloom too early and a late frost might damage delicate flowers and prevent seed formation. Bloom too late and pollinators might have moved on, or the growing season might be too short for seeds to mature. Many plants require specific weather conditions to complete their life cycle. Some seeds won't germinate unless they experience a cold period, ensuring they don't sprout in autumn only to face winter. Others need a period of heat or smoke from fire to trigger germination. Some plants depend on seasonal rainfall patterns, going dormant during dry seasons and growing quickly when rains return. Forests affect and are affected by weather. Trees release enormous amounts of water vapor through their leaves. A single large tree might release hundreds of gallons of water into the air each day. In large forests, this collective moisture release can actually contribute to cloud formation and rainfall. The Amazon rainforest, for instance, creates much of its own weather. Moisture evaporating from trees forms clouds that produce rain, which waters the trees, which release more moisture in an ongoing cycle. When forests are removed, local weather patterns often change. The area becomes drier and experiences more extreme temperatures. Rainfall may decrease or become more seasonal. The soil, no longer protected by tree cover and held together by roots, erodes more easily during storms. These changes can affect weather patterns downwind as well, since the forest no longer supplies moisture to the atmosphere. Seasonal weather changes trigger migrations in many animals. Birds fly thousands of miles to take advantage of abundant food in summer breeding grounds and mild winter conditions elsewhere. Monarch butterflies travel from Canada to Mexico and back again over multiple generations, each following weather cues. Whales migrate between feeding grounds in cold, productive waters and breeding grounds in warm, tropical seas. All of these movements are timed according to seasonal weather patterns that have remained consistent enough over evolutionary time for these elaborate behaviors to develop. The relationship between weather and climate is important to understand. Weather is what happens day to day. Today's high temperature, this week's rainfall, tomorrow's wind. Climate is the average of all those weather patterns over a long period, typically 30 years or more. It's the difference between saying, "It's unusually hot today," which is weather, and "Summers are getting hotter," which is climate. Earth's climate has always changed over geological time. Ice ages have come and gone. Warm periods have alternated with cool periods. These changes happened naturally, driven by variations in Earth's orbit, volcanic activity, changes in ocean currents, and other factors. But something different is happening now. The climate is changing faster than it has in thousands of years, and human activities are the primary cause. The mechanism is straightforward. Certain gases in the atmosphere, called greenhouse gases, trap heat near Earth's surface. The most important of these is carbon dioxide. When we burn fossil fuels like coal, oil, and natural gas, we release carbon dioxide that had been locked underground for millions of years. We've increased the amount of carbon dioxide in the atmosphere by about 50% since the Industrial Revolution. This extra carbon dioxide traps more heat, causing global temperatures to rise. Rising temperatures affect weather in several ways. Warmer air can hold more water vapor, so when storms form, they can produce heavier rainfall. A warmer atmosphere also means more energy available to fuel storms, potentially making hurricanes more intense. The pattern of where rain falls is shifting, with some areas becoming wetter and others drier. Heat waves are becoming more frequent and more intense. The warming isn't uniform across the planet. The Arctic is warming faster than anywhere else, a phenomenon called Arctic amplification. This is happening because as ice and snow melt, they expose darker ocean water and land surface that absorbs more sunlight, creating a feedback loop. The reduced temperature difference between the Arctic and the tropics may be affecting the jet stream, the high-altitude river of air that steers weather systems across the mid-latitudes. A wavier jet stream can lead to weather patterns getting stuck, causing prolonged heat waves or extended rainy periods. Sea levels are rising as glaciers and ice sheets melt, and as the ocean water itself expands from warming. Higher sea levels make coastal flooding worse during storms and can turn normal high tides into flooding events. Some low-lying coastal areas are already experiencing regular flooding during high tides that didn't cause problems in the past. Ocean temperatures are rising, and this matters for weather. Warmer ocean waters provide more fuel for hurricanes, potentially making them more intense. Changes in ocean temperature patterns affect atmospheric circulation, influencing weather across entire continents. Some of these changes may be altering the frequency and intensity of El Niño and La Niña events, which have worldwide weather effects. While no single weather event can be attributed solely to climate change, the changing climate is loading the dice, making certain outcomes more likely. It's like a baseball player taking performance-enhancing substances. Any particular home run might have happened anyway, but the overall increase in home runs is caused by the substances. Similarly, any particular heat wave or heavy rainfall event might have occurred naturally, but the increasing frequency and intensity of such events is driven by climate change. This doesn't mean every place will simply get hotter and drier, or hotter and wetter. Climate change affects different regions differently. Some areas may receive more precipitation, while nearby regions get less. Temperature increases are greater at high latitudes than near the equator. Nighttime temperatures are rising faster than daytime temperatures. Winter warming is more pronounced than summer warming in many areas. Understanding these regional patterns requires detailed climate models and careful observation. The science community has high confidence that Earth's climate will continue to warm if greenhouse gas concentrations continue to rise. The exact amount of warming and its specific impacts depend on how much additional greenhouse gas we emit and how quickly we transition to cleaner energy sources. But even if we stopped all emissions today, some additional warming would still occur because of greenhouse gases already in the atmosphere and because the ocean takes time to warm up. This doesn't mean the situation is hopeless. Every fraction of a degree of warming we prevent reduces the impacts on weather, ecosystems, and human societies. Renewable energy technologies are improving rapidly and becoming more affordable. Energy efficiency reduces how much fuel we need to burn. Protecting and restoring forests helps remove carbon dioxide from the atmosphere. Understanding how our actions affect the climate empowers us to make better choices. The weather you experience tomorrow, next week, and next year will still vary naturally. You'll still have some summers cooler than others, winters with more or less snow, springs with different rainfall. But underlying all this natural variability is a warming trend that makes extreme heat more common, heavy rainfall events more intense, and the overall character of weather somewhat different than your grandparents experienced. There's something quietly powerful all around you right now that you can't see, hear, or feel under normal circumstances. It's air pressure, the weight of all the atmosphere above you pressing down. At sea level, this pressure amounts to about 14.7 pounds per square inch. That means a column of air 1 inch square, stretching all the way to the edge of space, weighs nearly 15 pounds. Over your entire body, that's many tons of air pressing on you from all directions. But you don't feel crushed, because the air inside your body pushes outward with equal pressure. The force is balanced perfectly, so you don't notice the pressure at all. It's only when the pressure changes that you might become aware of it. Your ears pop when you drive up a mountain or take off in an aeroplane, because the air pressure outside your eardrum changes faster than the pressure inside, creating a temporary imbalance. Air pressure decreases with altitude. At the top of Mount Everest, the air pressure is only about 1/3 what it is at sea level. This is why mountain climbers need supplemental oxygen at extreme heights. There simply aren't enough air molecules per breath to supply the oxygen our bodies need. Even at more modest elevations, like the mile-high city of Denver, the reduced air pressure is noticeable. Water boils at a lower temperature, baked goods require recipe adjustments, and visitors from sea level might feel short of breath until their bodies adjust. But altitude isn't the only thing that affects air pressure. Temperature matters too. Warm air is less dense than cold air, so a column of warm air weighs less and creates lower pressure at the surface. This is why low-pressure systems are often associated with warm air and stormy weather, while high-pressure systems are associated with cooler, clearer conditions. Meteorologists measure air pressure with instruments called barometers. The classic mercury barometer, invented in the 1600s, uses a column of mercury in a glass tube to show pressure changes. When air pressure increases, it pushes down harder on a reservoir of mercury, forcing the mercury up the tube. When pressure decreases, the mercury drops. Modern electronic barometers use other methods, but they're measuring the same thing: the weight of the atmosphere. Weather forecasts often mention rising or falling barometric pressure, and for good reason. These pressure changes are excellent indicators of coming weather. Rising pressure usually means improving weather, clearing skies, and calmer winds. Falling pressure often signals approaching storms, increasing clouds, and potentially strong winds. A rapidly falling barometer is particularly ominous, suggesting a strong storm system is approaching quickly. The pressure patterns shown on weather maps tell a story. Lines called isobars connect points of equal pressure, much like contour lines on a topographic map connect points of equal elevation. Where isobars are close together, pressure is changing rapidly over a short distance, and winds will be strong. Where isobars are far apart, pressure changes gradually and winds will be light. The isobars often form circular or oval patterns around high and low pressure centers. High pressure systems, marked with an H on weather maps, generally bring pleasant weather. Air sinks in a high pressure system, becoming warmer and drier as it descends. This sinking motion suppresses cloud formation, leading to clear skies. Winds blow clockwise and outward from high-pressure centers in the northern hemisphere, counterclockwise in the southern hemisphere. These systems can persist for days, creating extended periods of nice weather. Low-pressure systems, marked with an L, are where weather happens. Air rises in low-pressure systems, cooling as it ascends. This cooling often leads to condensation, cloud formation, and precipitation. Winds blow counterclockwise and inward toward low-pressure centers in the northern hemisphere, clockwise in the southern hemisphere. Low-pressure systems are associated with storms, clouds, and unsettled weather. The strongest low-pressure systems, sometimes called cyclones, can produce severe weather including heavy rain, strong winds, and winter storms. The pressure at Earth's surface isn't uniform. Even without weather systems, there are semi-permanent patterns of high and low pressure. Near the equator, intense heating creates rising air and a belt of low pressure called the doldrums, or intertropical convergence zone. Around 30 degrees latitude north and south, descending air creates subtropical high-pressure belts. These are regions of generally clear skies and light winds, including many of the world's deserts. Near 60 degrees latitude, where warm and cold air masses meet, low pressure predominates. And at the poles, cold, dense air creates high-pressure regions. These pressure belts shift north and south with the seasons, following the sun. In summer, in the northern hemisphere, they shift northward. In winter, they shift southward. This seasonal movement affects weather patterns across the globe. The monsoons of South Asia, for instance, result from seasonal shifts in pressure patterns. In summer, low pressure develops over the heated land, drawing moist air inward from the ocean and bringing heavy rains. In winter, high pressure develops over the cooled land, and winds blow outward toward the ocean, bringing dry conditions. Changes in air pressure affect more than just weather. Some people with certain medical conditions can feel pressure changes as physical symptoms. Sinus pressure, joint pain, and headaches are sometimes triggered by dropping pressure. Whether this is due to the pressure change itself, to associated weather changes like increasing humidity, or to other factors is still being studied. But the connection between pressure changes and how some people feel is very real for those who experience it. Animals seem particularly sensitive to pressure changes. Birds, as mentioned earlier, often respond to falling pressure by feeding more actively before storms. Some researchers believe this is because birds can actually sense the pressure change directly, possibly through their inner ears or other specialized organs. Fish also respond to pressure changes, though for them, the pressure changes are transmitted through the water they live in. Pressure also plays a role in how sound travels. On a high-pressure day with clear skies, sounds often seem crisper and carry farther. This might be because the denser air conducts sound better. On low-pressure days before storms, sounds might seem muffled or distant. The changing density and humidity of the air affect how sound waves propagate. The changing seasons are such a fundamental part of our experience that it's easy to forget they're caused by something relatively simple: the tilt of Earth's axis. Our planet spins on an axis that's tilted at about 23.5 degrees relative to its orbital plane. As Earth orbits the Sun over the course of a year, this tilt means different parts of the planet are pointed more directly at the Sun at different times. In June, the northern hemisphere is tilted toward the Sun. Sunlight strikes the northern latitudes more directly, spreading each day's solar energy over a smaller area and making it more concentrated. Days are longer, giving the Sun more time to warm the surface. This is summer in the northern hemisphere. At the same time, the southern hemisphere is tilted away from the Sun, receiving sunlight at a slant and having shorter days. It's winter there. 6 months later, in December, the situation is reversed. The southern hemisphere is tilted toward the Sun and experiences summer, while the northern hemisphere, tilted away, experiences winter. This is why seasons are opposite in the two hemispheres. When it's summer in New York, it's winter in Sydney. The tropics, regions near the equator, experience much less seasonal variation because the sun's angle doesn't change as dramatically there. These regions have 1 or 2 seasons based on rainfall patterns rather than temperature. The temperate zones, between about 23 and 66 degrees latitude, experience 4 distinct seasons with noticeable temperature changes. The polar regions have extreme seasons, with continuous daylight in summer and continuous darkness in winter. Spring and fall are transition seasons when the sun's path is moving. The spring equinox, around March 20th, and the fall equinox, around September 22nd, are the 2 days each year when day and night are approximately equal everywhere on Earth. Equinox literally means equal night. On these days, the sun rises due east and sets due west, and the sun is directly overhead at the equator at noon. The summer solstice, around June 21st, is the longest day of the year in the northern hemisphere and the shortest in the southern hemisphere. The sun is directly overhead at the Tropic of Cancer, and it takes its highest path across the sky as seen from northern locations. The winter solstice, around December 21st, is the shortest day in the northern hemisphere and the longest in the southern hemisphere, with the sun directly overhead at the Tropic of Capricorn. These astronomical events drive seasonal changes in weather. In summer, the more direct sunlight and longer days warm the land and ocean. In winter, the slanted sunlight and shorter days provide less energy and temperatures drop. But the warmest part of summer usually comes weeks after the summer solstice, and the coldest part of winter comes weeks after the winter solstice. This lag happens because the land, and especially the ocean, take time to warm up and cool down. Seasonal changes affect every aspect of weather. In summer, stronger heating creates more instability in the atmosphere, leading to more frequent thunderstorms in many areas. The temperature difference between the equator and poles is less pronounced, which can lead to a weaker jet stream and more variable weather patterns. In winter, the stronger temperature contrast between equator and poles energizes the jet stream, creating stronger storms. Cold air masses plunge southward more readily, bringing cold snaps and winter storms. Different parts of the world experience seasons differently based on their latitude and proximity to oceans. Maritime climates, influenced by nearby oceans, have mild winters and cool summers, with relatively small temperature ranges. Continental climates, far from ocean moderating influences, have cold winters and hot summers with large temperature ranges. Mediterranean climates have wet winters and dry summers. Tropical climates may have distinct wet and dry seasons, rather than warm and cold seasons. The changing seasons bring migrations, hibernations, and life cycle changes in plants and animals. Trees in temperate zones lose their leaves in fall as days shorten and temperatures drop. This protects them from winter damage and water loss. In spring, warming and longer days trigger buds to open and new growth to begin. Flowers bloom in sequence, each species timed to take advantage of specific conditions. Animals breed in seasons when food will be abundant for raising young. Bears hibernate through winter when food is scarce. Birds migrate to take advantage of abundant summer food in high latitudes, then return to milder climates for winter. Even human societies are shaped by seasonal weather patterns. Agricultural practices developed around seasonal rainfall and temperature patterns. Traditionally, different foods were available in different seasons. Architecture in different climates reflects local seasonal challenges. Steep roofs in snowy regions, thick walls in hot deserts, large windows facing south in cold climates to capture winter sun. Though modern technology has reduced our direct dependence on seasons, we still feel their influence in countless ways. Weather forecasting has come an extraordinarily long way from ancient times when people relied on sky observation and folk wisdom. Today, forecasting combines satellite observations, ground-based measurements, theoretical understanding of atmospheric physics, and massive computer calculations to predict weather with impressive accuracy. The foundation of modern weather forecasting is observation. Around the world, thousands of weather stations record temperature, pressure, humidity, wind, and precipitation at regular intervals. Weather balloons, launched twice daily from hundreds of locations, carry instruments up through the atmosphere, measuring conditions at various altitudes. Aircraft report weather conditions during flights. Ships and buoys collect data from oceans. All this information flows into central databases. But the real revolution in weather forecasting came from space. Weather satellites, orbiting high above Earth, provide a continuous view of clouds, storms, and weather systems across the entire planet. Geostationary satellites hover over a fixed point on the equator, keeping constant watch over their portion of Earth. Polar orbiting satellites circle the planet from pole to pole, eventually covering every location. These satellites measure not just visible clouds, but also invisible water vapor, temperatures at various atmospheric levels, wind speeds, and much more. All this observational data feeds into computer models that simulate the atmosphere. These models divide the atmosphere into a three-dimensional grid of points and calculate how conditions at each point will change over time based on the laws of physics. They consider how heat moves, how air flows, how water evaporates and condenses, how different air masses interact, and countless other factors. The calculations are mind-bogglingly complex, requiring some of the world's most powerful supercomputers. Multiple forecast models run regularly, each using slightly different approaches or focusing on different aspects of the atmosphere. Meteorologists compare these models, looking for agreement and differences. When most models agree on a particular forecast, confidence is high. When models disagree significantly, uncertainty is greater, and forecasters must use their expertise to decide which model is likely most accurate. Short-term forecasts, covering the next few hours to a couple of days, are generally quite accurate. Meteorologists can predict with high confidence whether it will rain tomorrow, what the temperature will be, and whether storms are likely. These forecasts have improved dramatically over the past few decades. A modern 3-day forecast is as accurate as a 1-day forecast was 40 years ago. As we look further into the future, accuracy decreases. A forecast for a week ahead is less reliable than one for tomorrow. Beyond about 10 days, specific forecasts become difficult because the atmosphere is a chaotic system. Small differences in current conditions can lead to large differences in future weather. This doesn't mean we can't say anything about weather beyond 10 days. We can make probabilistic forecasts and identify broader patterns. But predicting whether it will rain on a specific afternoon 3 weeks from now is beyond current capabilities. Seasonal forecasts look at broader patterns over weeks to months. These forecasts don't predict specific day-to-day weather, but rather overall trends. Will this summer be warmer than average? Will rainfall be above or below normal? What are the chances of drought? These forecasts rely on factors that change more slowly than daily weather, such as ocean temperatures, soil moisture, and snow cover. El Niño and La Niña events in the Pacific Ocean, for instance, affect weather patterns across much of the world and can be predicted months in advance, allowing seasonal forecasts with useful skill. Severe weather forecasting has improved enormously, saving countless lives. Tornado watches and warnings give people time to seek shelter. Hurricane track forecasts allow coastal evacuations days in advance. Flash flood warnings alert people to dangerous conditions. These forecasts combine computer models with human expertise. Meteorologists recognize patterns and can predict that conditions are favorable for severe weather, even when models don't explicitly show it developing. Weather radar has been particularly important for severe weather forecasting. Doppler radar can detect not just where precipitation is falling, but also how fast it's moving toward or away from the radar. This allows meteorologists to identify rotation in storms that might produce tornadoes, to estimate rainfall amounts that might cause flooding, and to track storms in real time. Networks of radars provide coverage across populated areas, updating every few minutes. Despite all these advances, weather forecasting remains partly an art. Computer models are tools, but humans must interpret their output, recognize their limitations, and apply experience and understanding to create the final forecast. Good forecasters know their local area's quirks and typical patterns. They understand how models tend to perform in different situations. They can recognize when a forecast seems off, even if they can't immediately say why. This expertise develops over years of study and practice. Weather forecasting continues to improve. Satellites are becoming more sophisticated, measuring more variables with greater accuracy and resolution. Computer models are incorporating more detailed physics and running at higher resolutions. New sources of data, like GPS signals that are affected by atmospheric water vapor, provide additional observations. Machine learning and artificial intelligence are being used to find patterns in vast amounts of data. All these advances help forecasters see further into the future and predict weather more accurately. Yet, there will always be limits. The atmosphere is too complex, with too many interacting factors at too many scales for perfect prediction. Small-scale phenomena like individual thunderstorm cells or the exact track of a tornado will always be difficult to predict far in advance. But continued improvement in forecasting translates directly into saved lives and reduced property damage. Better warnings of severe weather give people time to prepare and protect themselves. Better forecasts of temperature and precipitation help farmers, utilities, transportation, and countless other sectors make better decisions. As we reach the end of our gentle journey through weather science, it's worth pausing to appreciate just how remarkable the atmosphere is. Every breath you take, every breeze you feel, every cloud you watch, every raindrop that falls, is part of an intricate system that makes life on Earth possible. The atmosphere is always in motion, always changing, always seeking balance while never quite achieving it. Energy from the sun drives everything, creating temperature differences that spawn winds, evaporate water, form clouds, and produce the endless variety of weather we experience. The rotation of the Earth adds its influence. The oceans store and release heat. The land shapes wind patterns. Living things interact with the air around them, and it all weaves together into something far more complex and beautiful than any simple model can capture. Weather touches every moment of your life in ways both obvious and subtle. It determines what clothes you wear and what activities you do. It affects your mood and your energy level. It fills reservoirs and grows crops. It shapes landscapes and influences the distribution of plants and animals. It created the conditions that allowed life to flourish on this planet, and it continues to sustain that life every single day. There's something deeply comforting about understanding weather, about knowing why the sky turns pink at sunset, or how clouds form, or what makes wind blow. It connects you to the world around you, helps you see that you're not separate from nature, but part of it. The same air that moves in wind through your open window is part of global circulation patterns. Same water that falls as rain in your garden has cycled through oceans and clouds countless times before. You are breathing atoms that have been breathed by every living thing that ever existed, all connected through this thin blanket of atmosphere that wraps our world. The science of weather continues to advance. Satellites orbit overhead, constantly watching clouds and measuring temperature, moisture, and winds. Computer models become more sophisticated, improving our ability to forecast what the weather will do days or even weeks in advance. Scientists probe the atmosphere with balloons, aircraft, and ground-based instruments, constantly learning more about how weather works. Yet despite all this knowledge and technology, weather retains its capacity to surprise and amaze us. Thunderstorms still produce lightning in ways we don't fully understand. Tornadoes form through mechanisms that remain somewhat mysterious. The exact track of a hurricane days in advance is still uncertain. Weather is a system so complex, with so many interacting factors, that perfect prediction may never be possible. And perhaps that's as it should be. A world of perfect predictability would lose something essential. So the next time you look out your window at a grey sky, or feel wind on your face, or watch clouds building on the horizon, take a moment to appreciate the science behind what you're seeing. Think about the water molecules evaporating from distant oceans, the differences in air pressure driving wind, the ice crystals forming in high clouds, the energy from the sun that powers it all. The weather isn't just something that happens to you. It's a magnificent planetary process in which you participate. And now, dear listener, our journey through the science of weather has come to its peaceful end. We've wandered together through evaporating oceans and forming clouds, felt the wind born from pressure differences, watched lightning split the sky, understood the fury of storms and the gentle beauty of rainbows. We've seen how everything connects: sun and water, heat and motion, earth and sky. I hope these facts have given you a deeper appreciation for the atmosphere that surrounds you, protects you, and makes your life possible. The next time rain begins to fall or clouds drift across the blue, perhaps you'll remember the science behind the beauty, and perhaps that knowledge will make it even more wonderful. You've done enough learning for today. You filled your mind with the gentle wonders of weather science, and now it's time to let all of that settle softly into rest. Close your eyes and imagine yourself as a single water droplet, rising gently on warm air, floating peacefully through a cloud, and then slowly, gently falling as rain, returning to the earth to begin the cycle again. Around and around, up and down, the endless peaceful cycle of water and weather. Let your breathing match the rhythm of waves on a shore. In and out, steady and calm. Feel yourself relaxing more deeply with each breath, like clouds dispersing on a summer afternoon. Your body is heavy and comfortable. Your mind is quiet and peaceful. The science of weather will be there tomorrow if you wish to ponder it further. But for now, there is only this moment, this breath, this deep and restful peace. You are safe. You are comfortable. You are exactly where you need to be. Let sleep come as naturally as rain from a cloud, as inevitable as wind following pressure, as peaceful as morning fog lifting from a valley. You have done enough for today. Close your eyes, rest deeply, and dream of gentle weather. Sweet dreams, dear friend, and thank you for spending this time with me. Until we meet again, sleep well.